Hi everyone, we're going to take a look at our next video in our Unit 1 on sequences and series. This particular section is the geometric series, section 4. Our objective is to take a look at the geometric series, try to figure out what the formula might be, and then work with our formula a little bit in a variety of examples. As you are listening to this lesson, please make sure that you watch out for the definition of the geometric series. And other than that, you should be fine with the vocabulary that we're using as we go through this unit. So, based on your understanding of the arithmetic sequence and series, what is the geometric series likely to be? And I think if you stop and think about it, you know that an arithmetic sequence is a pattern of numbers. This arithmetic series is when we take those numbers and add them together. And likewise, the geometric sequence is a special pattern. And when you take the numbers in the sequence and add them together, you're creating something called the geometric series. In a geometric series, it's the expression for the sum of the terms of a geometric sequence. So, thinking of a formula for the geometric series, this one is a rather unusual one to come up with. And so, we're going to start by looking at the logic, but we're actually going to take a look at a simple example. And I'm going to show you a sort of the process that we go through to get to the general example. So, we're going to consider a very simple geometric sequence where it's a gossip chain, where each person tells two persons. So if you think about what's happening, you've got the beginning person, they tell two, those guys tell two, and so on down through the chain. So the numbers in the sequence are 1, 2, 4, and then we have 8. So if you think about this geometric sequence that we have this number where we're adding it all up and trying to say, okay, what is this going to add? The sum of four numbers, if you will. I've got the first person, the second term, the third term, and the last term. So the question is, how do we go about doing this? So I'm going to show you the way that we do it to actually derive the general term. And I'm going to use it with this very simple sequence so that you can understand what's going on. I know that the sum of the first four terms is 1 plus 2 plus 4 plus 8. And now what I'm going to do is take this particular one and I'm going to multiply it by 2, or the ratio. And that will give me 2 plus 4 plus 8 plus 16. And I'm going to put these two together. I'll put the one that was multiplied by 2 on top and the one that is the ordinary one on the bottom. And I'm going to subtract them. So now you'll notice that these numbers in the middle disappear and that all I have is the last number minus the first one. And basically, if you think about what you have here, you've got the sum of the four terms of the ratio, that's the 2. Remember, it was stood for the ratio. It's the r minus 1. Now, I don't want to know what the sum is of the ratio minus 1. I want to know just the sum of those four terms. So I'm going to divide both sides by the r minus 1. So I'll get 16 minus 1 on top and the r minus 1 on the bottom, which is 2 minus 1 in this case. And what I'm getting is 15. Now, if you look at the numbers, of course, you know they're 15 already. But it's sort of curious that we found it this way. That is the way that we go about it for the general term as well. So let's try to take a look at it. Here's the general form of the geometric series. Sorry, I'm moving around too much. So I'm going to write my sum as the first term plus the second term plus the third term and so on, all the way down to the last term. And then I'm going to multiply everybody inside of here by another ratio. So you can see my numbers come off this way. Stopping to think about this one, if I multiply by one more ratio, it's like having r to the n minus 1 times r to the 1, which turns into r to the n. Okay, then I'm going to subtract the two. So I start with this one minus this one. And so what I get, essentially all these guys in the middle disappear, and I'll have the last one minus the first one. So you can see there's the last one minus the first one. And remember, what I was doing here was finding the sum of the nth number of terms of r minus 1. So I'm going to divide both sides by that. And so if I take a look at what I have here, I'm going to factor out the t1. You can see that. And I'm left with minus 1 plus r to the n. And that, other than just flipping those spots, is the formula for finding the nth term. So the sum of an n number of terms is the first term times the ratio to the power of that same n minus the number 1 and on the bottom, r minus 1. And there you have it. Now let me make sure this is okay. Yeah, this looks fine. The only thing is that there's a little bit of a problem with my subscript. This is not a subscript. This T1 should be down here. It's the first term times the ratio to the power of n minus 1. And just keep in mind that your ratio cannot be a 1. If it were a 1, then we would get an undefined answer, and so we cannot use it at all. So here we go. Let's give it a try. Determine the sum of the first 10 terms of the geometric series. Okay, let's take a look. So my first term is 4, my ratio is 3, and the number of terms is 10. So the sum of 10 terms is the first term, 4, times the ratio, which is 3 to the power of 10, minus 1 over 3 minus 1. And your number, when you put it all in your calculator, is the following. So please don't assume that you know how to put this into your calculator. Please practice this. Next one, where my first term is 5 and my ratio is 1/2. Okay, now they still want the number of terms to be 10. So my first term is 5, my ratio is 1/2 to the power of 10 minus 1. And then down the bottom, 1/2 minus 1. And my number is still written as a fraction is the following. Thank goodness I can say for calculators. Okay, determine the sum of each geometric series. So I've got the first term. I can see that to go from one to the other, I appear to be multiplying by a 3. And I have this number as the last one, so I don't know what that is. So here I have my first term, I have my ratio, and I don't know how many terms it is. So first I'm going to stop. I'm going to take this number and figure out how many terms it is. So I use my formula, put the first term in, the ratio, multiply it by 27, get both sides written to the power of 3. You might want to stop and take a closer look at this a little bit carefully. And then it looks like if this is a 3 and this base is a 3, then 9 has to be n minus 1. So n is a 10. So they want us to find 10 terms again. So then we plug everything in, our first number, our ratio to the power of 10, filling in all the other numbers, and we get this very messy looking fraction. Now, you can use an alternate formula as well. And this one I'm just giving to you at this point that S of n is equal to the ratio times the last term minus the first term and r minus 1. Now, if you're interested in this next slide, I've actually shown where this alternate formula comes from. I'm not going to take the time right now to actually talk about it, but if you're interested, pause the video, take a look at it so that you can see where this formula came from. For now, we're going to pretend and use it. So we know the ratio is 3. We know the last term was 7/29. Our first term was 1/27. Our ratio is 3. And sure enough, we get the very same answer. So it depends on the scenario and the situation which formula you would be best to use. Okay, this one tells us actually to use the alternate formula for this one. So let's take all those numbers. And we know the first term, the ratio, the last term. We plug in our numbers. It really is as simple as that. Plug it in, put it in your calculator, and you will find the sum. So a real life example. We're going to be taking a look at an organization that actually promotes the game of Scrabble. Now, what it does is it offers internet tournaments throughout the year. So you can sign up to be a part of a playoff, basically. The losers, it's very simple. You play a round of Scrabble with someone online. The losers of each round are eliminated until a final match is played. So let's assume there are 256 entries. What is the total number of matches that will be played in the tournament? Well, you would start with 256 entries. Now, that means that there are only half as many matches. And so the first number in your term will be 128. And everyone after that is being divided by 1/2 because someone loses until you get to the point where your last term is 1. Someone has 1. So we use our formula and we can bop things out and we find out that they have promoted definitely the game of Scrabble because 255 matches have been played. Now, in closing, I just wanted to show you a very important example of what is considered a natural series found in nature. Now, fractals are a mathematical idea that began a long time ago, and it's basically based on a pattern that is self-repeating. It repeats over and over and over infinitely. One of the most famous fractals is the Mandelbrot fractal, named after the man who created it. And basically, what you're seeing here is, let's call it a black snowman. And then if you were to zoom in closer to this one, you would be seeing the same black snowman. And then if you were to zoom into this little guy on the side, you're going to see the same black snowman and this little guy and this little guy. And supposedly, if we zoomed into this guy and came in like on a rocket ship, even closer to it, then all of these little guys that are coming off the side of it would also be the black snowman. This is a fractal, a self-repeating pattern. Now, the cool thing about it is that fractal-like behavior happens as well in nature. This is a kind of broccoli or cauliflower, I should say. And so if you look at it, all of these florets that have these kind of patterns are repeated when you get down to the tiny ones, and then to the very tiny ones, and to the tiny, tiny ones. It's an amazing example of a self-repeating pattern in nature. Even a tree, in a very basic kind of way, you have the spine of the tree that breaks off into the spine of a smaller one and back into the spine and into the little tiny branches in here and then into the leaves. And it just keeps going on and on. And so we call this fractal like behavior. And the person, here's someone who's tried to use an actual pattern to make a tree based on a self repeating pattern of a fractal. Anyway, that's an introduction to an interesting branch of mathematics. But our purpose in this one was to derive the formula for and work with a geometric series, actually. That should be series. I'm just seeing a mistake. And here is your homework. So this will help you get ready and to practice the various types of questions that you need. Make sure that if anything gives you trouble that you seek out an answer. Good luck, everyone.